We're on our last section. It's going to take us today and Monday to do it, right? These are the main topics and that is in that section. That leaves us 3 days, which is 1 day more than I thought you were going to get because I planned for the last 2 days, but looks like it's going to be the last 3 days. But that's not a problem because we can use that time to get ready for the final. So if you want, you know, we can spend a whole day or half a day just solving trig equations, or maybe practicing more in doing the algebra of identities, right? Playing about with those and seeing what we've got. So it's, if I had a choice, I'd be much happier the way we are than, hey guys, we're going to have to work up to the last minute of Thursday just to cover the work. That would be not so much fun. Okay, so here we go. Deals with a thing called the dot product. So you've got two vectors, I'm calling them u and v. And the components of this guy, its x component is u1, u2 is its y component, and there's the same thing for v. And this thing here is one version of the dot product. It's the one that's most commonly used. And it says that the cosine of the angle between the vectors, which is this guy here, can be found by the dot product divided by the two magnitudes. And the dot product is what you get when you multiply these together, and then you multiply these. And you can actually extend this to three-dimensional vectors, which I kind of accidentally did yesterday. Theoretically, you know, you can extend it to 10-dimensional vectors, which nobody has a clue what that looks like, but theoretically you could do it. So the things we're going to look at are basic stuff like finding the angle between two vectors, and we'll be doing a few examples of different kinds of that. Then we're going to look at, we're going to test to see if two vectors are parallel. Then we're going to test to see if two vectors are right angled. And then we're going to use the dot product and other things to find all the sides and angles of a triangle PQR when all you're told are their coordinates. And lastly, we're going to do an application, which is finding the work done. If you've ever done, I think it's physics, if you've ever done those questions where you pull a block up a sloping hill and you want to know how much work's done, that kind of thing, that's what this is like. So that's our kind of hit list of things to do. So let's start with calculating or finding the angle between two vectors. And I'll scroll up, got all the questions here. Okay, this question 3. U is the vector 6, 0. V is the vector 2, 9. And we're being asked to find the dot product and then the angle between them, theta. So I might as well just do that first. It's question A. And so that's 6 times 2, add 0 times 9. And that ends up being 12. Now, to get the angle, we use this formula here. And it's normally written this way, even although later on we do some more to it. So I guess I need to find what the magnitude of u is. Are you happy with the answer being 6? I don't actually need to calculate it. Why? Because isn't 6 a long and none up 6 units? This one here, I will calculate it. It's the square root of 2 squared plus 9 squared, which I believe is the square root of 85. So the cosine of the angle between them is the dot product, which is 12, divided by the magnitude of this one, which is 6, times the magnitude of the other one, which is 85. And then if you want to find theta, you can do it all in one go on your calculator by finding the inverse cosine of this ugly fraction. So I go over my calculator and I make sure that I'm in degrees because I keep changing. This time I am, that's good. I'm going to do the inverse cosine of 12 divided by, put a bracket around it to make sure these two get multiplied first. And the answer I get, what do they want? Nearest degree, great, I like it when they do that. So the missing angle is 77 degrees. And when you do these questions, you do not need to worry about the angle that the calculator gives you might not be the one you want. You really only do that with things like, you know, the inverse tan guy, inverse tan of y over x, that one. That you have to be sure you know which quadrant you're in and that your angle is, when you're finished, between 0 and 360. That's a pretty straightforward one, just to get the ball rolling. So if you did these two vectors on square paper, that angle here would be about 77 degrees. The next one, I'm choosing because of the way the question is written. They're using IJI notation. I is 1 in the x direction, j is 1 in the y direction. I don't like this notation because I'm far too careless for my own good. 1 in the x, √5 in the y. So I transfer it to this notation, which I just feel easier to deal with. And negative √5, 1. Are you comfortable with the transfer? That even if the question is written using IJI notation, I'd prefer, me personally, I prefer component form, which is these guys. Well, let's find question A, which says find the dot product. In this case, it's going to be 1 times negative square root of 5 plus square root of 5 times 1, which ends up being 0. Now, I could go through find the magnitude of this vector, which, by the way, happens to be √6, and I could find the magnitude of this guy, which is √6, and I could plug it all into here, but I don't need any of that because this is a very special case. If the dot product is 0, what angle are you guaranteed is going to be between the two vectors? If the dot product is 0, what angle is going to be between the two vectors? We talked 90. About this, 90, yeah. So one of the properties of a dot product is, if the dot product is 0, the angle between the vectors is 90. If the dot product is positive, the angle will be an acute angle, right? 0 to 90. And if the dot product is a negative number, the angle between them will be bigger than 90, right? It'll be an obtuse angle. But the 0 is the useful one. So that one's finished and we're good. And try one last one. A rather strange one. Well, it's not really 5, it's just, I'll pick my one. And I don't know why I'm calling that B, I'll call it B, right. So I want you to imagine that you're told the vector is A, 3A, and the other vector is B, negative 2B. And we're going to see, right, what the dot product is, right, and see how far we can get the answer. So we won't be able to tell a degree, perhaps not, but we'll try and do as much as we can. So let's do the dot product. You can do it because it's A times B, add 3A times negative 2B. And that's AB, take away 6AB, and that ends up being negative 5AB. Are you comfortable about how I found the dot product, even although it's not really numbers, it's variables? But don't I do the same thing as if it was numbers? So far, so good? Do you think I'll be able to find a number for the angle between these two vectors, even although this is A's and B's? Do you think I'll be able to do it? Some of you think so. We're going to find out. The magnitude of vector A is the square root of A squared plus 3A squared, which is the square root of A squared plus 9A squared, which is the square root of 10A squared. So far, so good? Can you simplify that? Or let's phrase it a different way. What do you simplify that down to? Because it can be simplified a little bit.
10A, right?
Yeah. Square root of 10A. Oh, by the way, we'll make the assumption that A and B are positive, right? Which is reasonable. Now let's find the magnitude of this guy. He's going to be B squared plus negative 2B squared. So that's going to be B squared plus 4B squared, which is going to be the square root of 5B squared. What does that guy simplify to?
B times the square root of 5.
Okay, square root of 5B or B square root of 5. Now I'm going to put in our formula and see where it leads. It's the dot product divided by the magnitude. Looks like that. The dot product is negative 5AB. This guy is square root of 10A, and this guy is the square root of 5B. If I do a little bit of tidying up here, won't those two give me the square root of 50AB? So with me?
And then can't you just essentially cancel the A and B?
And even although we did not have numbers, didn't we have A's and B's everywhere, even although we started there, didn't we end up with not having any? Which means then that shouldn't I be able to find the angle between them? On our calculator then, the inverse cosine of negative 5 divided by the square root of 50, and I get, wow. I wasn't expecting such a nice answer. I knew I could get an angle, but I wasn't expecting a perfect 135 degrees.
Will we be able to get answers for all the questions with variables instead of numbers in the vectors, or just some of them?
Just some of them, unfortunately.
Okay.
It depends on how they go. So I'll tell you the ones that will work. If these are only got A's in them, right? 4A, 10A, 7A, right? Not A plus ones or anything, right? Just multiples of A, and this one has multiples of B, then it will work, right? If you say A plus 2 or 3A minus 1, right? If you add a number in, this won't work, right? If you mix the A's and B's up, so that's 2A and that's 4B and that's 3A and that's 7B, right? Things like that, it won't work. But as long as these only have multiples of A and these have only multiples of B, this will happen. And you might wonder, why does it work? Well, let me show you. Here is U. If I pull out a common factor of A, isn't it just a multiple of the vector 1, 3? Right? Just like a common factor, right? Pull it out. Now, if you take the vector V, which was B negative 2B, and you pull out b as a common factor, isn't it just a multiple of the vector 1, 2? Now, if you take a vector or its multiple and another vector and its multiple, it doesn't really matter. Isn't the angle between them still going to be the same whether you make them bigger or smaller? Because all you're doing is making them longer. You're not changing, how they point. Does that make sense why that particular combination works? You're really just doing some version, some multiple of this vector, meeting up with some multiple of that. And so they meet at a single angle, in this case 135.
So if we would have used the vectors without A and B in them, we would have got the same answer.
You would have got exactly the same answer. If you've got time, check it. It would be 135 degrees. So it's the same answer, yes. Kind of interesting little side issue. So I feel comfortable that I've covered enough, but that's what I think isn't important. It's what you think is more important. Are we okay with number 1? If I gave you 2 vectors, do you feel comfortable that you could find the angle between the 2? Do you want to see more, or do you feel good with that? I got a thumbs up. Okay, so I'm checking it off my list. Last chance to change your mind. If you want to see another one, just tell me. If you've actually got one that you're looking at on the screen and you want to see it, I can do that too. Okay, that seems to be everyone's happy. Let's move on to our second topic for today. Testing to see if 2 vectors are parallel. So, imagine I have a vector u and I have another vector v. They could be parallel, right? Right, they go in the same direction, just one might be longer than the other. Okay. So how do you test to see if 2 vectors are parallel? Well, you use this fella. And you use them in the same way that you use it for all things. You find theta. Now here's the tricky part. Hopefully it's not too tricky. What will the angle between 2 vectors that are parallel? What will the angle be? What number?
180.
Correct. What other number? There is a second value that also means that you're parallel.
Pi.
360.
Well, go the other way. It's kind of 360, but I'd rather you chose the small version of 360. Zero. Right, visually, let's talk about the 2 vectors. I'll make them green and red, right? Can you imagine the green one is that guy? Would the angle between those 2 vectors be 0? Right, the red and the green. Can you imagine one on top of the other? That's what 0 looks like. Now, what does 180 look like? Well, if you pick a point and U goes this way and the other one goes the other way, can you see that the angle would be 180? And you might say, wait a minute, they're pointing in different directions, which I agree they are, right? But the direction you point in a line has nothing to do with them being parallel. Can't 2 lines be parallel and point different ways? One can point uphill, the other can point downhill. Aren't they still parallel, right? They're the same distance apart, essentially. So if you can get an angle of 180 or 0, you know that you are looking at parallel lines. So I'm going to do some examples of those and see if we can do it. I have a vector 2, -6, and I have a second vector which is going to be 1, -3. And I'm going to prove that those 2 vectors are parallel. And magnitude of u ends up being 4 add 36, square root of 40. magnitude of V ends up being 1 plus 9, which is the square root of 10. Are you okay with me doing that in my head? That's a 2, by the way, right? 2 squared plus 36, right? 4, 36, 40. 1 and 9 get me 10. Now the dot product is 3 times 1 plus negative 6 times negative 3. That's 3 plus 18. That is 21. Excuse me, I'll be back very shortly. Sorry about that, everyone. It's been that kind of day where nothing is as it should be. Okay, so cosine theta dot product divided by,
Is that 20 or 21? Because I think U is 2
Oh.
to the -6.
thank you. That could make a big difference because my answer won't work. Glad someone's paying attention. Right. So the inverse cosine of 20 over those two things. Right. And let's do it. Inverse cosine 20 divided by, put a bracket around it, square root of 40 times square root of 10. Isn't it nice when things come out good? And doesn't 0 degree mean the two vectors are parallel? Oops. Now, there is a way, well, there are two ways I could check this. Let me try and show you both methods. One is just visual. So the first vector, right, I'm just going to pick a random spot, and it's 2 to the right and 1, 2, 3, 4, 5, 6 down. So that would be a visualization of you. And then I'll pick a different spot. It doesn't really matter where I pick. I'll pick here, and I'll go 1 along, 1, 2, 3 down, and I'll pick that guy, and I'll call him V. If I put little pens on top of them, I don't know if that helps. Would you agree they look parallel? Great. Make them a bit longer if you have to visualize it. That's one way to do it. Here's another way to check. If two vectors are parallel, then one vector will be a multiple of the other. Would you agree if they're parallel, isn't this one just 2 times that kind of thing? So let's look at the two vectors I've got here. Isn't U 2 times the vector V? Check that out. If you double this guy, don't you get this guy? So we go with it? So hopefully have I convinced you that the dot product does check and tell you. Why don't we draw it? Why don't we look at a multiple? Can you imagine that you could have two vectors that are quite small when you draw them, and they might look parallel, but couldn't they just be like, 92 degrees and 93 degrees, 1 degree out, but you'd never notice it because it's such a small thing. So visual checks aren't really good because it's hard sometimes to tell if they really are parallel. Multiples can work, but sometimes the multiples aren't nice multiples. Couldn't you get a thing like U is 17, 19 V, right? Can you imagine that multiple? I doubt you'd be able to guess that by looking at the values. The grade would just be too weird. So this is infallible because the answer is 0 or 180. It is parallel. So I'm going to give you one to try it. Well, actually, I'm going to give you two to try it. One of them is going to be parallel and the other one isn't. And we'll see if we can find them. So in no particular order, here is the two vectors. And this is the second one. And pick this guy as 1, 8. And I'll pick this guy 4, 32. Actually, I'll make it -4, -32. Yeah, that's more interesting. And this one's going to be 3, 4. And this is going to be -5, 12. Okay, you won't probably have time to check both.
I have a quick question.
Yes.
In Desmos, can you do the triangle brackets or whatever it's called and graph it like that? Or does it not understand?
I haven't even tried to make it do it, but I doubt if it can do it, is my guess.
You basically just put both of the equations as like coordinates. That's basically how you do parametric equations, because they have like a weird section called the parametric calculator, graphic calculator, and they basically just show it to you. You basically just take both of the equations. Oh, am I thinking of something else? I think I am.
Right. Okay. But it's
thinking
worth
of something
looking
else.
at. I haven't got time, but you probably have hopefully more time than I have. Just do a search like Desmos vectors and see if someone's figured a way of doing it. Right. You got 4 minutes from now. Pick one and do it. That's probably all the time you've got. If you're really fast, you might get the second one. So pick whichever one you like.
Yeah, if you search up Desmos vectors, it comes up with one.
So
and
it
you
does
just
have a way
change
of
the
doing.
numbers. Yeah, all you have to do is change the numbers and it works.
Cool. You can have a play about with that and try some of these. Just thinking, you could get some blank paper where you left spaces here and here. And couldn't you set this up so that when you do one of these questions, this is already printed for you and just fill in the gaps? Kind of what I'm doing here. Okay, here goes for it. Anybody find which one of those two is actually the one that's parallel? One or two? Which one's parallel?
It would be 1.
It is. And 2 is not. So, dot product. 1 times -4. 8 times -32. So -4, 240, 256. I believe that's -260. Okay, I need that number. So it's going to go here. Magnitude of this one is the square root of 65. Magnitude of this one is just too hard to do. So it's going to be a 4 squared, add a 32 squared, and I get 1040. I'm not even worrying about can I simplify them. This is a calculation question. So if it's just a calculation question, you can leave them alone, save you some time. Right, so theta is the inverse cosine of this guy. And I believe it's 180 degrees. Is that what you got? 180? Let's see. Inverse cosine, -260, divided by square root of 65 times a square root of 1040. You need another bracket. Let's bring this bad boy back up. I got inverse cosine, nice to check. Divided by check, square root of 625, check, times that guy. I think I need a third one. No. Okay, why am I?
No, you forgot one where it says square root of 65 plus.
Oh, okay. So easy. Here, right? So
Yeah.
insert a bracket. Now I probably need to take one out because I'll have too many. Right, try that one. There we go. Third time lucky. And the angle you got was 180 degrees. And that makes them parallel. Okay. This one should be the one that isn't. So it's going to be 3 times -5 plus 4 times 12 which is negative 15 add 48, which I believe is 33. So 33 going to go there. The magnitude of U is 5. Magnitude of V is 13, or the square root of 25 and 163 if you want. And so theta is going to be the inverse cosine of, I can do them because they're nice numbers. So inverse cosine of 33 divided by 65, and the answer you get is about, we'll call it 59 degrees to nearest whole number. So those two vectors are definitely not parallel. They meet at an angle of 59. The first two vectors are parallel, and they point away from each other, but they're still parallel, and that's because their angle is 180. Are we good with that type of question, or do you want to see another one? If I gave you two vectors, could you tell if they're parallel or not by using dot products? I'm working alone here, guys. I kind of need a thumbs up or
So I have a quick question.
sad face.
Magnitude
Yes.
is the length of the line, correct?
Yeah, it's the length of the vector.
Okay.
Right. Anything else, or can I assume that we can move on? Okay, we'll do that then. The next one's going to be really short because we've kind of covered it, but I want to do one just for completeness sake. And the next one in my little list, where's my little list? There it goes. So we've done that one. This one's going to be quite quick. Testing to see if two vectors are at right angles. Now, if two vectors are going to be, put that one down, 3, two vectors, or, well, there are various names for them, so right angles. Perpendicular is quite a common phrase to use, means the same as that. Has anybody heard of this one? Because it does appear in some textbooks. Orthogonal. You ever heard of that term? Two vectors are orthogonal. It means that they're at right angles, right? It means they're perpendicular. If you were visualizing it, one of your vectors might be this guy, and the other one would be that guy there. And this angle is 90 degrees. Well, that's true. If the dot product is 0. So that's going to be easy to check, right? Just find the dot product. If it's 0, they're orthogonal, right? They are right angled. They are perpendicular, whatever phrase they want to use. It means the same thing. So let's just pick two examples, one where it is and one where it isn't. Suppose I had a 3, 4, and the other one was negative 8, 6. And we were being asked, is it perpendicular? And the way they phrase them in the homework is, there are two choices, yes or no. Will you please not just pick one, and if it's wrong, pick the other one? Really do practice at it, because when you do a test, the final exam in particular, you're going to have to prove to me that that's yes or no, right? You're going to have to show me why you know that's the case. So it's not a big calculation anyway. The dot product here is 3 times negative 8 plus 4 times 6, which is 0. So you would say yes. Dead easy, right? Are two things perpendicular, two vectors perpendicular? If their dot product is 0, you're going to say yes. And for completeness sake, I'm only going to do one of these guys. if you do the dot product, in this case of these two vectors, you get 1 times -2 plus 7 times -1. You get -2, take away 7, you get -9. And so won't your answer in this case be a no, it's not. I mentioned at the start of today, if the dot product is negative, right, in this case, -9, although you don't know the exact value of the angle, what range of values must it be in? Theta has to be in what range if the dot product is negative?
Isn't it less than 90?
Or, move my little hands on if you can see me, I'm going like this, right? Or, the opposite, or it's bigger than 90. So, put this down. If the dot product is positive, then theta will be less than 90, right? If the dot product is negative, theta is actually going to be, how would I write that? It's going to be bigger than 90. In fact, the biggest angle that you can get between two vectors is 180 degrees. Now you might say, well, you could have a vector going this way and you could have a vector going that way. That angle is bigger than 180. Well, I guess that angle is, but isn't the angle between them always this one, which is guaranteed to be less than 180, or at most 180, but when it's 180, they're parallel. So if I gave you two vectors and I went and said to you, are these two vectors, I'm trying to think about right angled, perpendicular, do you feel comfortable you could check? Right, if I gave you two vectors and I said, are they right angled, would you be able to do a check and say yes or no? Do you feel comfortable about that question? Okay, then I'll cross that off my list. The next question are long. So I'll only have time to do one of these, and when we see you next week, we'll start here and do some more. Imagine I tell you the coordinates of three points, P, Q, and R. And I'll try and sketch them. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3. So here is R. Q is 3, -2. So here is Q. And R is 1, 2. I should say here is P. So what you're going to get here is a triangle, typically. Agreed? We are going to use a lot of the things that we've found in vectors, and we are going to find the length of these guys and the size of these angles. In other words, everything that you could possibly want on that triangle. And we're going to do it using vectors and dot products and all sorts of other things like that. So first thing I'm going to do.
Technically, if you found all the sides, couldn't you just use the cosine rule?
Well, guess what? Isn't the dot product a kind of cosine rule?
I
It
mean,
gets you the,
I haven't analyzed it, so I don't know. But
yeah, it is really. It's just a different version of the cosine rule. It's a rule that allows you to find an angle using a cosine, right? It's a kind of connected to that. You certainly could do it that way. we're just going to do it using dot products. It's just as quick. So first thing I'm going to do is I have to figure out how we're going to put these vectors together. So I'm going to go PQ and PR. I'm just going to focus on those two vectors right now, right? PQ and PR. Now, the vector joining P to R, right? There's P and there's R. Can you remember the formula? It went x2 take away x1, y2 take away y1. But the quick way to do it is second guy take away the first. 7 take away 1. 3, right? Second take away the first. There's PR. PQ. Second guy, take away the first. 3 take away 1 gets me 2. -2 take away 2 gets me -4. Are you comfortable with what I just did there?
How did you determine the direction of the vectors? Does that
Well,
matter?
It does matter as long as both vectors leave P. So I've decided I'm going to pick P, and so I have to go PR and I have to go PQ. It does matter. If I did PR and QP, I wouldn't actually be finding this angle. I'd be finding this big angle here, which is not the one we want. So randomly pick a P, Q, or R. It doesn't matter which one of those you pick. But once you're committed, in my case, to P, make sure the other two go PR and PQ. Let's just pretend I liked Q, right? But if I wanted to do Q, the two vectors I would use would be QR and QP. Because can you see QR and QP would show me the angle at Q, right? Won't this one tell me the angle at P when I'm finished? So there is a logic to it. So it's not just anything. You could choose anything to start with, but once you're committed to a corner, you have to follow a certain rule. Now, in this guy here, the magnitude of PR is the square root of 37, and the magnitude of PQ is 16, and 20 is the square root of 20. So I'm actually going to draw a triangle here that's meant to represent the same guy. And every time I find something, I'm going to write it into this triangle. I have just found out that the length of PR is the square root of 37. And I've just found out the length of PQ is the square root of 20. Agreed? Right, the magnitude of the vector joining P to R, right, it's the length. And so the magnitude of that is the length from here to here, the distance PR. Now I'm going to do the dot product. And in this case, it's going to be 6 times 2 plus 1 times -4, which is what, 12. Take away 4, it's 8. Okay. So the cosine of theta is the dot product divided by the magnitudes. The dot product is 8, and the two magnitudes are square root of 37 and square root of 20. So theta, which is essentially angle P, is going to be the inverse cosine of those guys. So inverse cosine, 8 divided by, put a bracket around it, square root of 37, remember to close that bracket, times square root of 20. Remember to close that bracket, And one more or two more. That'll do. Let's do it to the nearest whole number. So I'm going to call that 73 degrees. So I now know that this guy here is 73 degrees. Now, there are a number of different approaches to finishing this question now. I think it was Aidan, but it might have been someone else who went and said, couldn't we use the cosine rule? Would you agree the cosine rule works really well with that triangle? Couldn't I find this side here? Right. But actually, couldn't I find this side here by just finding the vector RQ and getting its magnitude? So I could have done it that way, right? Nothing wrong with either of those two methods. If I wanted to find angle R, well, after I found this length, couldn't I get angle R by using the sine rule? And couldn't I find angle Q again using the sine rule? That would be one approach, and that would work totally fine. Couldn't I use dot products? Right. Suppose I wanted to find this angle up here. I'm going to call it theta. If I wanted to use dot products to get this angle, wouldn't I have to do RP and RQ? Do you see I'd have to find two different vectors? But couldn't I do this and get the answer? Now, I don't know the answer to that, and I don't have time to calculate it, so I'm going to pretend I did know the answer. Can we pretend that this answer was 30 degrees, just for argument's sake? And we've already found this guy, and let's just pretend it's a square root of 50, although I don't know what it is. How would I get the last angle? I've got all three sides now, and I've got two angles. How do I get
Do
angle
180 minus 73 minus
Yep.
30.
Yeah, that's it. And I believe that would be 77. So can you see this question involves a whole load of stuff and different methods to do it, right? You could use dot product all the way. You could use dot product and then cosine rule, then sine rule, for instance, is another way. Put your name down for attendance last time, and bye-bye for now. And I will see you tomorrow. No, I won't. I will see you on Monday.
Will we do more of these problems on Monday?
Oh God, yes.
Okay.
I know they take for ages, but there's a lot in it, so you do need to see it. And I only had time to get halfway through, so I really want to do a couple of these. That way I can tick it off my little box and say we've covered it and get work done.
Thank you.
None of this is in this week's homework or this week's test, right? So don't worry about anything to do with dot products. I think I've left it online so you can do some homework if you want to get a head start, but that's totally up to you.
Thank you.
Thank
Bye.
you.
Bye-bye for now. Aidan, you have any questions for me? No, you're just saying bye-bye now? Okay.